Let's talk about the theory of continental drift. Why don't we look at a world map? Have you ever seen one of these? Well, of course you've seen one of these. Everyone has seen a map of the world. In fact, you probably first saw a map of the world when you were in kindergarten. And what you may have noticed, similar to so many people before you, is that if you look carefully at the continents, the giant land masses covering about 29% of the Earth, if you look at them carefully, they almost look like puzzle pieces, like they fit together. Especially if you look at certain parts of the world, like the eastern coast of South America and the west coast of Africa, for example. They look like they belong together. Now, I hate to break your hearts, but this is not a groundbreaking discovery. In fact, people have known this for hundreds of years. Most people have just taken it for granted that that's just the way the continents look. But there have been a few brave scientists throughout history who have thought that it must be something more. Let me introduce you to one. This is Alfred Wegener. Alfred Wegener was a German meteorologist. He studied weather. He lived in the late 1800s and early 1900s. And as a weather person, a scientist of the atmosphere, of course, Wegener spent a lot of time looking at maps. And so he noticed this strange shape phenomenon just like you did. The problem is he couldn't get past it. He actually devoted his whole life to it. He came up with a radical theory that suggested that the continents were actually once connected and then somehow ripped apart to where they are today. He came out and he said, "I think the continents are moving." Of course, people thought this was kind of a silly thought to have. How could a continent possibly move? But Wegener really thought that this was the case, and so he devoted his whole career to studying this and coming up with proof of this radical idea. In fact, Wegener didn't just think the continents were moving. He actually believed that there was a time when they were all connected, and they have since drifted apart to their current locations. He even came up with a name for that supercontinent that existed in the past. He called it Pangaea, the supercontinent that he believed existed about 250 million years ago. Pangaea, or Pangaea, is actually an appropriate name. It's a Greek term that means entire Earth or all Earth. So if you think about it, when all the continents were together, if Wegener is correct, it would make sense to call that landmass Pangaea or Pangaea. Here's what he thought it looked like. You can see within this diagram the modern-day continents of North America, Africa, South America, Antarctica, India, etc. But they don't look quite the same way they do today. And of course, they're in totally different positions, all connected into this one supercontinent. Now, people thought Wegener was a little bit nutty. And so he knew that if he was going to make any headway with this idea, he had to come up with evidence. And so we're going to take a look at 4 pieces of evidence that Wegener put together to prove to the public that the continents had in fact drifted. Let's take a look at his first piece of evidence. We'll go back to this map here. Now, the first piece of evidence we've actually already discussed. It's simply the observation that the continents appear to fit together. As simple as that. Wegener didn't believe that this could be simply a coincidence. He feels like there's no possible way the continents would have this appearance just randomly. And so this becomes evidence number 1. We will call it the apparent fit of the continents, the fact that they look like they fit together. And just to expand on that a little bit, essentially the coastlines of the continents appear to fit together, kind of like the pieces of a puzzle. But that's not enough. So Wegener went back to the drawing board. He dug through piles of books and libraries and became quite interested in fossils and other evidence of prehistoric life. In fact, Wegener became particularly interested in that guy who just swam across the screen, the Meza Soros. Now let me tell you about the Meza Soros. This is an ancient reptile that lived only in shallow fresh water. What's interesting, though, is that there's only 2 places in the world where we find fossils of this freshwater creature. One place is the eastern coast of South America, and the other is the western coast of Africa. Now, there's a couple possible solutions for this. Now, either the Meza Soros was living on one of these continents and somehow learned how to fly across the Atlantic Ocean to inhabit the other side of the other continent. But that's not likely. The Meza Soros certainly could not fly. And we know the Meza Soros couldn't have swam across. The distance is just too great, and they can't survive in salt water. So that's out of the question. Maybe the water was frozen and he walked across? Well, that's a possibility, but there's really no evidence to support that. And so what Wegener said is that while the Meza Soros roamed the land, Africa and South America were connected, and they were able to freely walk across the land masses. And then after going extinct, the land masses were torn apart and separated, carrying some of the fossils to what would become South America and some to what would become Africa. Interestingly, Wegener looked into this and found that there were other organisms that lived in the past that had similar fossil distributions. Cynonathus, Lystrosaurus, and Glossoteris being amongst the more notable ones. These fossils all have these very unique distribution patterns that suggest that the continents were once together. And in fact, if you reassemble the continents and map out the locations of these fossils, they line up perfectly. So that's our evidence number 2. We call it fossil correlation. Correlation simply means matching up. So matching up fossils on either side of the ocean. To summarize, identical fossils have been found in the rocks on either side of the ocean, and therefore the continents were once connected and must have drifted apart. But Wegener knew he needed a stronger case, and so he went back to the library yet again and became fascinated by rocks and geologic structures like mountain ranges of the past. And he found a really interesting pattern, not unlike what he found with fossils. In fact, if we go back to our world map here, and let's zoom in on the North Atlantic here, if you look at the mountain ranges in the northeastern United States and the mountain ranges in northern Europe, they match up perfectly. And what I mean is that they are made of the same type of rock and the same age of rock. Now, of course, anything is possible, and the same exact rocks could have formed in 2 different locations at the same time. But geologically, that's unlikely. A better explanation is that these mountains were once connected, and as the continents moved, they tore them into 2. And that becomes evidence number 3. We call it rock or mountain correlation. And what we see is that identical rocks and mountain structures have been found on either side of the ocean, suggesting that the continents were once connected. But we need one more, and this is probably the most complex of them all. Again, Wegener returned to the library, and this time he returned to his roots as a meteorologist, and he began to look at past climate data, meaning he looked at evidence of cold and warm weather in different parts of the world, and he found something fascinating. See, he first looked into glaciers. So glaciers are these giant rivers of ice that move slowly across the Earth's surface. And of course, glaciers have to be found in cold parts of the Earth. Today, they're restricted to only the highest mountaintops and, of course, the north and south poles of the Earth. Something interesting about glaciers is that they move. And when they move over the rock beneath, they leave evidence in the form of scratches that we call glacial striations, which you see here. Now, how does this relate to continental drift? Well, if we look at our map, if you look in the present-day tropical rainforests of South America and Africa, you will find glacial striations. Here, in these 2 regions, you find these scratches in the bedrock. Now, if you think about that, how could there be glaciers in a tropical rainforest? Unless it wasn't always a tropical rainforest. This suggests that these continents were not always in their warm equatorial regions like they are now. They were once down near the South Pole where it could have been cold enough to have glaciers, and they have since drifted apart. But Wegener wanted more from this climate data, and so he began to explore a little deeper. And that's when he came across this rock. This is a sedimentary rock called bituminous coal. We know it because we burn it for energy. It's a fossil fuel. What we know about bituminous coal, if you were to look in earth science reference tables, you would see that bituminous coal is made from compacted plant remains. So picture tropical plants like this dying on this forest floor and getting compressed over millions of years to form coal. Now let's look at where coal is found on Earth. Anywhere you see this little icon, we have found coal deposits. Now let's think about this. Coal forms from tropical plants, yet it's found in Antarctica, in northern Europe, in northern Asia, and the southern tip of Africa and Australia, and in the northern United States. These are not tropical climates. yet they have coal, which is evidence of a past tropical climate. And so this, just like the glaciers, suggests that the continents have moved over time. And that becomes evidence number 4, paleoclimate data, or past climate data. The observation that coal has been found in cold areas, and that glacial evidence has been found in warm areas. And with these 4 pieces of evidence, Wegener published his book, The Origin of Continents and Oceans, in which he laid out his case for continental drift, suggesting that all the continents were once connected in a supercontinent called Pangaea, which existed about 250 million years ago, and since the continent has ripped apart into the present-day landmasses that we know so well. Later in his life, Wegener took an expedition to the North Pole, and in this expedition he wanted to gather more evidence to support his theory of continental drift. Unfortunately, on a very cold, dark, stormy day, Wegener set out on an expedition to gather food for his colleagues, and he never was heard from again. Wegener died of exposure and was frozen in the ice, and his body is actually still there today, frozen forever. The sad thing about that is that Wegener was never able to explain what made the continents drive, what made them move, what made the supercontinent rip apart. And so he died before his theory would become accepted by the scientific community. He never got to see his life's work come to fruition. That's the story of continental drift. Thanks for listening.